Hey folks, so I just have a few quick housekeeping announcements sort of things that I wanted to go over before we kind of get into today's discussion. So first off, hopefully you all saw, but your third and final notebook check was due this last Tuesday by 5 p.m. But remember that you can still turn in notebooks late. It'll just be like 3 points a day. And notebooks are a really easy way to boost your grade, and they shouldn't be a ton of hassle if you've been staying on top of that stuff. So I highly recommend, if you have not gotten your notebook in, to do that as soon as possible, because you could still get a good percentage of the points. The other thing that I wanted to talk about is your final exam. So your final exam will be Wednesday, and that will be available kind of same as your quiz for 24 hours, starting 8 p.m. Wednesday the 13th until, 8 a.m. Wednesday the 13th to Thursday the 14th at 8 a.m. Okay, so just kind of want to make sure you're staying on top of that. Mr. Weber will upload a practice exam, same as the other ones, for you guys to look through, and that will be available Sunday through Monday. So make sure you do look at that. I will probably try to post a formula sheet as well for you guys to look over. Make sure you're familiar with all the formulas that you'll need to use for the exam. But I'm probably not going to post much past that. But if you guys do have any questions, have any problems you're working on that you need help on, feel free to shoot me an email. Along that same note, during finals week, I'm only going to have office hours on Monday. My office hours are the same as they're going to be, 1 to 3 p.m., but just on Monday. I'm not going to hold a review session or anything, and I'm not going to post a video. But if you guys want help, have any questions before the exam, you'll still have my office hours Monday from 1 to 3 p.m. Okay, so I'll probably try to post an announcement about that, so you can drop in, ask me questions. If you've worked on the practice exam before then, feel free to stop on in and ask me any questions about that. But as always, you can still shoot me an email, whatever you would like. And that was kind of the bulk of what I wanted to go through. The last thing that I would say is please, please, please remember to fill out evaluations. I can't remember the numbers exactly, but I believe if we have over 80% or more student evaluations in, everyone will get 2 extra credit points, which is really, really nice. Everyone could use that boost with everything going on. So please remember to fill out evaluations, and do that for Mr. Weber's main lecture, but also for discussion as well. I really appreciate the feedback, and I really like to go through and see if anyone has any things that they liked, things that they didn't, things that they wished would be improved on, and whatnot. So please try and fill those out as soon as possible. I think they're due pretty soon, maybe Sunday at midnight, I want to say, Sunday or Saturday. Regardless, please fill those out. But those were just a little bit of announcement, housekeeping things that I wanted to go through, and now we can get into the section. Okay, so let's actually get into the section. So I have a lot of things that I want to try to go over, but we are going to do it. We're going to get through it, okay? So first and foremost, let's just go through what the fundamental theorem of calculus tells us. So remember that when we are taking an antiderivative, so whenever we have this integral sign, we're taking an antiderivative. When we take an antiderivative of a function, we get this other function, which we define as cap f of x. So this is our antiderivative, which we call cap f. Okay. Now the fundamental theorem of calculus tells us that when we are looking at the integral over an interval, say a to b, so this interval is a to b, write it in interval notation here. And this is actually looking at the area under the function. When we're looking at this integral from a to b, that simply equals the antiderivative cap f of x evaluated at the rightmost value of the interval, so the end of the interval, minus our antiderivative at the beginning of the interval, which is so nice and so easy to use. So now, rather than doing all of those rectangles and summing things up and finding a bunch of areas, we have a really quick and easy formula, okay? So I am just gonna box that bad boy in because that is super, super important. Okay, so we call that our fundamental theorem of calculus. We don't capitalize the O because of isn't capitalized. Okay, so that's what we're really talking about this section, is how to use this theorem to find the area under graphs. So it's super nice, super easy to work with, okay? And along with that comes some additional components, which you might have already saw in 12.4 that we didn't really go over in discussion. So if your interval, like the bounds are exactly the same, say you're going from a to a of f of x dx, that just equals 0. Because think about it, when you're doing your rectangles, you would have a width of 0. So when you're trying to calculate that area, it's width times height to get area of a rectangle, right? So when you're finding that area, you have a width of 0 times whatever height. It's going to be 0. So that's really nice. So anytime you see these insanely complicated functions that you're just like, oh my gosh, I don't even know how to approach this, step back and look at the integration bounds for a second, because if they're the same, you don't have to do any more work for it. You just evaluate that to 0 and then you're done. It'll take like 2 seconds. It's a really nice and easy problem. Just remember to look at your bounds of integration. Okay, other couple of things that we have is if we want to evaluate from a to b dx, this is the same thing as evaluating from b to a of f of x, with one extra catch. Now it's negative. When we're flipping our bounds of integration, when we're going from a lesser value or a higher value to a lesser value, that's going to be the same area but the negative of it. Okay? Because you're going in the opposite direction. So you have to have that negative sign. Ooh, we're going to keep trying to scroll down. Okay. And then the other one is you can break up integration into smaller pieces. So you can look at this in either direction. Okay, so say you have a function, it's kind of tricky, you don't know what's going on from A to C, but you do know what's going on from A to B and then from B to C. So you can go in either direction with this guy. And it just makes it a lot easier to try to evaluate some functions by using this, by breaking an interval up into little sub-intervals. The caveat is these values have to be the same. It doesn't work if you have two different values there. Okay? So that should be all of the general things that we want to go over today. So let's actually get into some problems and actually look at some of these. Okay? So, and remember, we're still just using our regular old integration rules. So let's actually maybe write those down again. So that we have those for reference. Okay, so I'm gonna scroll all the way up. You can tell I don't write evenly, but that is fine. So we have our reverse power rule. That one is x to the n plus 1 over n plus 1. And we can't forget our plus c. And then we have integral of e to the x dx, and that is just itself plus c. And then integral of 1 over x dx, that is equal to natural log absolute value of x plus c. Kind of ran out of room there, so I'm going to make this a little bit smaller because it does not need to be that big, because that is just review. We're just using it as reference. Okay? Cool, cool, cool. So now let's actually look at some problems. So I'm not really going to focus too much on specifically problems you guys were assigned, just kind of overall, just how does this stuff work, how can we use it kind of thing. So let's just start off with a pretty simple to the point one. Let's look at problem 17. Okay, so like I said, this isn't a problem that you guys were assigned, but I mean, it's just the content, it's just the material. You want to make sure that you're knowing how to do this. So we have x squared dx, and that is from 2 to 5, okay? So first and foremost, we want to identify which of these rules we want to use, and you know, if you guys were here, I would ask you which one we want to use, but I'm just going to assume you're following along with me, taking guesses as I do. And given that we have this power here, we're going to want to use the reverse quote-unquote power rule. Okay, so we're going to be using this guy. So we get x, our n is 2 here, so we'll have 3 over 3. Now, when we have actual bounds, oops, maybe it'll let me, actual bounds of integration here, we don't have our plus c. Because think about it this way, we would have f at b plus c minus f at a plus c, but these c's are the exact same value, they're the same. So they just cancel out. So then we still have f at b minus f at a. Okay, all of those constants just cancel out. So we can just drop them right from the get-go and not worry about them, which is pretty nice. So we get x3 over 3. And now I'm going to put this vertical bar to say evaluate it out. Remember when we were doing implicit differentiation, we used this vertical bar to say evaluate it at a point. Same kind of idea. I'm going to say we're going to evaluate at 2 and at 5 and do the difference between those two. Okay, so we get 5 cubed over 3 minus 2 cubed over 3. So 5 cubed, that's 125, minus 2 cubed is 8 over 3. Oof, mental math. Give me a second. I think it'd be 117 over 3. Just did that off my head, so you might want to fact check me on that. And you guys are more than welcome to use a decimal. You just know I prefer fractions. And that's all there is to it. It's pretty straightforward and to the point. So now we know that if we were to actually graph this bad boy, remember x squared looks like that, and from 2 to say 5, we know that the area, oops, we're just going to squish that 5 in because it's not included. We're just going to say it's right there. We now know that the area here is 117 over 3. So that's pretty amazing, right? We didn't have to do any rectangles. We didn't have to do any area calculations. We were able to get the area just by using the fundamental theorem of calculus. So you will definitely hear me geeking out for the rest of discussion about this theorem because I have used it throughout the entirety of my math career. And it is just so useful and so convenient. So I am a fan of the fundamental theorem of calculus. Okay, so that was using the reverse power rule. Now let's look at another one using a different rule. If this will erase. Sometimes it doesn't even want to erase for me. Okay, so let's look at 19. We're just going to kind of go through all of the rules really quick here. So we have 1 over x dx. And this is from 1 to 3. Okay, now, same as before, if you were here, I would ask you, but we're all in our own homes, very separate from each other, so we're going to use this rule right here, because we have 1 over x. So we get natural log, absolute value of x, and drop our plus c, and we're going to evaluate from 1 to 3. One note here is our interval is from 1 to 3, so that gives us that x is always greater than 0. So this means that we can drop our absolute value. Okay, so just something to kind of remember. You don't need the absolute value in there if you know that your x is always greater than 0, because that's the main thing that we need. We need x to be greater than 0. That's why we leave the absolute value symbol in there. So then this gives us natural log of 3 minus natural log of 1. And maybe you guys remember this, maybe you don't, but we have a property of natural logs where when you are taking, well, not just natural log specifically, but any log, when you are taking logs with the same bases and doing a difference, you can convert that to a quotient. Okay, so something kind of nice to use to do a little bit of mental math in your head. We get natural log of 3, oopsies, natural log of 3 over 1 is just equal to natural log of 3. And you can find the decimal if you would like to, but I'm just going to leave it as that because it just makes a little bit more sense in my head. Okay, so we have looked at our reverse power rule, we have looked at the one with natural log, now let's look at one with e. So we have practice with all of them. So let's look at 23. So we have integral of 2e to the x from 0 to 3. I'm really a fan of these 3's. Okay, dx, don't want to forget that dx, and we are going to be using this guy now. And remember, nothing happens with that coefficient, same as with derivatives, we can just leave coefficients as they are, so we get 2e dx, oopsies, evaluated from 0 to 3. And that gives us 2e cubed minus 2e to the 0. Remember that e to the 0, that just equals 1. So then we get 2e cubed minus 2. And I'm actually just going to leave my answer as that, because I don't have a calculator on me right now. So that's really all that I need to do for that problem. Okay, cool. So we have kind of gone through the basics here. Now let's get into some stuff that's a little bit more interesting, a little bit more involved, okay? So let's look at how u substitution works with these definite integrals. So, okay, with u substitution, there's kind of two different ways to go about it, and it is completely your preference which one you want to use. So either, and we'll do two different problems so you can kind of see it either way. But either you can do a u substitution and change your bounds of integration into terms of u, or you can just go through the integral, change it to a indefinite integral, and then once you get everything back into terms of x, then you bring in your bounds again. So that probably doesn't make a ton of sense right now, so let's actually look at some problems so you can see what I am talking about. Okay, we can look at problem 37. Again, this wasn't one that was assigned, but you can still get the gist. So we are looking at the integral of 12 x squared minus 4 to the 5th x dx, and this integral is from 2 to 3. Okay? So before you panic, before you say anything like, oh my gosh, what is going on? Let's rewrite this integral first and foremost so we can kind of get a better view of it. So we can do 2 to 3 x squared minus 4 the fifth dx. Okay, and I left out my coefficient for a reason. So I kind of know in the back of my mind that I'm going to do a u substitution. This step is optional, let me say. But since I know that I'm going to be doing a u substitution, I'm going to kind of write my coefficients differently. So bear with me for a second here. So I'm going to leave a 2 inside the integral and bring a 6 outside of the integral. And you can double check me. 6 times 2 will still get that 12. But I want that 2x still inside the integral so I can do a u substitution. Okay? So now that we have this rewritten, it looks a little bit more manageable, right? Hopefully. So remember, you want to choose your u to be whatever is more complex or whatever kind of has the higher power. Okay, so in this case, our higher power is this x squared minus 4. So we want that guy to be our u. So we're going to say u equals x squared minus 4. And then that should give us that our du is 2x. So do you see now why I left that 2x in there? 2x dx. Okay, very cool. So we have that this guy right here, that is our u, and this 2x times our dx, that is our du. Okay. So let's look at this two different ways. Let's change our bounds first. Let's look at that one. And let's look at say switch to in-depth integral. I'm trying to make this as readable as possible for people that only look at the notes. Okay, so let's do our changing bounds first. So I'm going to move that up a little bit. So what that means is we're still going to have our integral 6. We're going to have, remember that's these two together, 2x times dx, that's our du. And this x squared minus 4, that's our u. So we're going to have u to the 5th times du. Okay. But see how I didn't write my integration bounds? That's because they're going to be different. So we're going to have u and u. And we're going to plug in these two bounds into our u equation. Okay? So we're going to plug in 2 for this lower bound. So we have 2 squared minus 4. And we're going to plug in 3, and that's going to be our upper bound, 3 squared minus 4. So 2 squared, that's 4, minus 4, 0. 3 squared, that's 9, minus 4, that's 5. So my new bounds are 0 to 5. Okay? So I took my bounds, because these bounds are in terms of x, and I switch them to be bounds in terms of u. Okay? Actually, move this guy over a smidgen. Okay. Now that we have that, I can just treat my integral like I would normally. So I'm going to leave this 6 out here. We'll have u to the 6 over 6, because we're doing our reverse power rule, remember? And now we're going to evaluate from 0 to 5. And I can already see right away those 6's are going to cancel out. So then we're just going to have 5 to the 6th minus 5 to the 0. Now anything to the 0 power is just 1. So we get 5 to the 6th which is not an easy number to do in my head, so I will probably have to calculate it. Okay, so I got 15,625 minus 1, which is 15,624. Okay, and I did not do mental math, I simply plugged it into a calculator. Okay, and that's our final answer. So if we wanted to, we could rewrite it. So we would say, just gonna bring this down a little bit, we would say integral from 2 to 3 of 12 x squared minus 4 to the 5th x dx, that equals 15,624. Okay. Now let's go back to our other method, which is switch to an indefinite integral. So to do that, we're gonna, same as before, write it out with our u's, u to the 5th du. But what I'm gonna do here is I'm just gonna drop my bounds for a second. I'm just gonna be like, okay, we're just gonna ignore that this is actually a definite integral, and we're just gonna quickly switch it to an indefinite integral and hope, nobody notices, because, who checks their work, whatnot. So we're going to quickly switch it to an indefinite integral and do like we did before. So we're going to have 6u to the 6th over 6, but I know in the back of my head that I'm working with a definite integral. So because of that, I'm not going to include my plus c. Even though we switch things to an indefinite integral, I know that we're working with a definite integral, so I'm not going to include my plus c, okay? But now we have done everything we need to. These 6's can cancel, so we put it back into terms of x. So we get our x squared minus 4 to the 6th, and now we bring in our bounds of integration, okay? Now we say this is going to evaluate from 2 to 3, okay? So we get 3 squared minus 4 to the 6th minus, 2 squared minus 4 to the 6th. Okay, so 3 squared minus 4, we already said that is 5, so we get 5 to the 6th. Oh, oops, sorry, I just realized I did this wrong over here. This should be 0 to the 6th. That is just 0. Oops-a-daisy. Glad I caught that. However, ironically, if it was 0 to the 0, I think it would be 1. Might want to double check me on that. But then that should still be 5. Oops-a-daisy. Okay, got that fixed. And again, over here we'll have 2 squared, which is 4, minus 4. That's 0 again, so minus 0 to the 6th equals 15,625. So we got the same answer doing it the same way. So it really is just a personal preference which one you want to use. Okay, because you get the correct answer either way you do it. Okay, so we saw one doing it that way. Let's actually look at one that was assigned to you, and then I have one more topic to go over, and then I will let you guys go. I am actually going to try to record a Chapter 12 review video really quick after this, and hopefully get that uploaded ASAP, because I know some people had some questions on quiz 17 and quiz 16, and I didn't want to include that with the 12.5 video, but I still did want to go over that material and go over a couple other things that I didn't have a chance to in previous videos. So I'm gonna record that really quick, get that uploaded as soon as possible, but I'm gonna try to be brief with this one. Okay, so let's look at one more problem doing a U substitution. So let's look at problem 45. So you have integral from 0 to 1 of x e to the negative x squared dx. Okay, so what do you think we want our u to be? So remember, we're kind of looking for the same things we did with chain rule. We're looking at powers, we're looking at exponents, and we're looking at denominators, okay? So in this case, we have an exponent being this e to the something, okay? And we have a term that has a higher degree than our other x term. So we want our u to be whatever is in that exponent. So we want u to be negative x squared. So that gives us that du is equal to a negative 2x dx. Okay? But we don't have a negative 2x dx. So what we need to do is divide both sides by a negative 2. So we get a negative du over 2 equals x dx. You cannot do this with variables. You can only do this with coefficients. So say you had x squared here instead, and you were like, oh, well, all I'm missing from du is an extra x, so I'm just going to multiply this by x. You can't do that. First answer, it's just kind of wrong. Second answer, though, is you want, when you're switching over to u substitution, you want everything to be in terms of u, okay? So it doesn't make sense to introduce an additional x in there that doesn't work with the integration values. Okay, so we don't want any x's in when we're doing a u substitution. So now we have that this guy right here, that is our u, and this x times this dx, that is our negative du over 2. Okay, so we can do integral e to the u times negative du over 2. Okay, I'm just going to change that to, oopsies, I'm going to rewrite that differently, negative, and I forgot again. Negative 1/2, I wanted to bring that 1/2 out to e to the u du. Okay? So here, again, it's personal preference whether you want to change your bounds or switch to an indefinite integral. I'm going to change my bounds because I think you probably have the least amount of practice doing it that way, if that way was introduced at all. So I'm going to actually do it that way. So we have u equals negative 1 squared and u equals a negative 0 squared. So we get 0, we get a negative 1. Okay. So 0, negative 1, and 0 and negative 1. So I'm going to use one of our rules of integrals that we introduced way at the beginning, which is this guy right here. If you are going and if you want to flip your bounds of integration, you just add on a negative sign. So if we go all the way back here, my bounds of integration are not the way I would like to go. They're from 0 to negative 1. So from a greater value to a lesser value. So I'm going to switch those bounds of integration. But when I do that, I need to multiply by a negative 1. So doing so, I get 1/2 integral negative 1 to 0 e to the u du. And I'm just going to put in parentheses switched order of bounds. Okay, now I can just do my integration. So we have 1/2 e to the u from negative 1 to 0, which is 1/2 e to the 0 minus e to the negative 1. Now e to the 0, we already said that is just going to be 1. So we have 1/2, 1 minus, and anytime you have something to a negative exponent, It's the same thing as just putting it in the denominator with a positive exponent. So this is e to the first. Okay? And I'm actually just going to kind of leave my answer that way. If you were looking for a decimal, you can just quickly plug that number in. But that's all that we really needed to do for that problem. So hopefully the combination of these two problems has kind of cleared up how you need to do definite integrals with a u substitution. That was kind of the bulk of that. The last thing that I wanted to go over was average value over an interval. Okay, so remember, recall from 9.7 that your average value of a function was just the function over x. Okay, but now we want to say average value of a function over an interval. Okay, so that is 1 over the width of our interval, how long our interval is, times a definite integral. That is our average value of f of x over an interval, okay? So try not to get these two confused. They are two different values and they're calculating two different things, okay? So keep that straight. When you're asked for just the average value of a function, you're looking at this expression, okay? When you're asked for the average value over an interval, this is really the key part here, this over an interval. That's where you want to use this equation, okay? Okay, so let's try a problem with this. So you had problem 81 was a application problem, a word problem. So let's look at that one really fast. So you have, oh, I lost it for a second. S of x equals 10 e 2x minus 1. And you want to find, and this is your supply function, you want to find the average price in dollars over the interval 20 to 30. Okay, so you're looking for an average price over the interval. Okay, and this is its price and its supply. They don't really specify that a ton, but this is our function. We want to find the average value of this function over this interval. That's all they're really saying. Okay, so we're going to use this equation here. We're going to say average val, and this over the interval, that's specified, but I just don't want to write that every time. So I'm just going to say average val, okay, try to keep that straight, b minus a, integral a to b, f of x dx, and what is our interval? Well, it's this guy right here. So we're going to have 1 over 30 minus 20, integral from 20 to 30 of s of x dx. So that is 1 over 10, integral 20 to 30. And now I'm actually going to write what our function is. So we have 10 e to the 0.02x minus 1 dx. Okay. we can see already that this 10 and that is going to cancel out. So then we get 20 to 30 e to the 0.02x minus 1 dx. Okay, so I can see that I'm going to have to use a u substitution for that guy there. But to do a u substitution, I need the integral broken up into its smallest parts possible. I cannot have additional terms in the integral if I'm doing a u substitution. So if I have any addition or subtraction, I need to break up that integral into addition and subtraction of integrals, because I can't do that with a u substitution. So I'll show you what I'm talking about. So I want to do a u substitution on that guy there. So I'm going to do 20 to 30 e to the 0.02x and then dx, and then I'm going to subtract integral 20 to 30 of 1 dx. Okay, so now that I have these broken up into two integrals, now I can do a u substitution. Because if I try to do it with this guy still in that integral, I would get a u and the substitution wouldn't work out correctly, and we just don't want that, so we just want to break it up into its parts right away. So now we can say u equals 0.02x, du equals 0.02 dx. We don't have that, so we're going to divide by it on both sides. So this decimal right here, let's write this over here maybe, is the same thing as 1/50th, and this part isn't totally needed, but when we're dividing by 0.02, it's the same thing as multiplying by 50, so I can rewrite that as 50 du equals dx. And it's not crucial that you guys know that. You could just do it with the decimal, but I just prefer to work without them whenever possible. So I'm just going to write this really, really small over here. 50. Okay. So then I can say integral e to the u times 50 du. So it's a little bit nicer to work with now. And this guy I can just leave as is. I don't need to do anything there. Got ahead of myself. dx. Okay. So I can leave one integral with u and I can leave the other one with x. And I'm going to switch my bounds again. So I'm going to do u equals 0.02 times 30. And u equals 0.02 times 20. Let's say those are my bounds. Okay. And we get 3/5, which is 0.6. And we get 2/5, which is 0.4. Okay, so I'm gonna have to move down here a little bit. So I can say 0.4, 0.6, and now we have 50 e to the u evaluated from 0.4 to 0.6 minus x from 20 to 30. Okay. This is all just plugging in numbers and whatnot, so I might just kind of set things up and leave it here for you guys, because as you have seen from the rest of this, I don't really have a calculator on me. So we have 0.6 minus 50 e to the 0.4 minus 30 minus 20, which gives us 50 e to the 0.6, is 50 e to the 0.4 minus 10. and that equals about 6.51. So their average price is over the interval 20 to 30 is $6.51. Okay, so that was everything that I wanted to touch on today. If there is anything that you guys are still a little bit fuzzy on, please reach out to me, especially before the quiz, before you take the quiz if possible. Reach out to me if you have any questions. And yeah, so that should be, you guys should be very good, very prepared for the quiz. And I'm going to try to get that review video posted as soon as possible. But yes, have a good rest of your day and good luck on your quiz and honestly the rest of your finals.